start this one. Okay, so today we are jumping into acids and bases, and acid-base solutions mostly. And before we really move any further, the first thing we have to do is define an acid and a base. Now you guys will remember, oh, I need more space. Lots more space. Okay, you guys will remember way back in chapter 6 when we first introduced chemical reactions. We said, hey, we can represent acids and bases by saying that you have some substance which contributes an OH and substance which contributes an H, and when you put them together you make water. So for instance, and this is again from chapter, I think it's from chapter 6, but it's whatever, it's the chapter on chemical reactions. If it seems like they move around those chapters every edition. But if I had like a HCl, and that would be aqueous, and then NaOH, and that would be aqueous. And the H goes with the OH because this is that double displacement reaction. It makes HOH, otherwise known as H2O, which is a liquid. And the Na goes with the Cl, which they're both +1 -1, so we can write it like that. And I'm gonna put a little, saved it there so I could make a subscript. You guys remember this, right? And this was your acid, and this was your base. And we saw that the acid plus the base would always make water and some sort of salt. Okay. This is a great definition of an acid, but it's a little bit simple. So on this chapter, we're going to expand upon that, right? So in this case, this is what we call the Arrhenius definition of an acid or a base. And that is, the acid is an H+ donor. That's not right. The acid increases the concentration of H+ in the solution, and the base increases the concentration of OH- in solution. Okay, in this chapter, we're just going to expand upon that a little bit more. So here we are in chapter 10. I'm going to title this. Okay, so in this lecture, in chapter 10, what we're actually going to do is define them just a tiny bit differently. This is called the Bronsted-Lowry definition of acids and bases. We're going to say an acid is any species which is going to donate an H+ ion to another molecule or ion. We might call this a proton donor. You'll hear this terminology. The reason we call it a proton donor is that the hydrogen atom, remember, it only has one proton and one electron. And so if you remove its electron to make it positive, all that's left is a proton, right? So it donates an H+, and an H+ is a proton. And so we'll call it a proton donor. And then the base then is the species which will accept the H+ from another molecule. And so going back up to the equation that we saw here, according to the Arrhenius definition, this was the acid because it increased the amount of H+ in solution, and this was the base because it increased the amount of OH- in solution, and then those H+ and OH- in solution, they reacted with each other to make water. We come back up with the same, we're still going to call it the acid and the base, but we'll say the acid is donating the H+ to the OH minus. And the base here, the OH minus, is accepting the H plus from that HCl. Does that make sense? Okay, so how can you tell if something will act as an acid or a base? This is something that you're going to have to do on the test. So general considerations based on these definitions here. I hope you can see that you cannot be an acid if you don't have a hydrogen ion to donate, right? If there's no hydrogen in the molecule, you won't be an acid according to these definitions, right? So one consideration, all acids have a spare H plus. Now I say, well, I say spare because a molecule might have a hydrogen and not be willing to part with it, right? If it's not willing to donate the hydrogen that it has, then it's still not an acid. So to be an acid, you have to have a hydrogen and you have to be willing to give it up. So if you're willing to give it up, we'll say it's kind of like it's a spare hydrogen that can be removed by an external species. Okay, so you might say, how do I know if a hydrogen can be removed? Well, there's a couple guidelines you can follow here. For instance, any polyatomic ion that you're familiar with, like so the nitrate or the phosphate or the sulfate or the sulfite, all these ones you memorized way back for our second exam, and yeah, you still have to know them. If you stick a hydrogen on there, that is a hydrogen that can be removed because the polyatomic ion is a thing. It's happy all by itself, relatively speaking. It's okay if that hydrogen leaves. Does that make sense? Okay, additionally, all the halogens are acidic when bonded to hydrogen. So this is too much red for me. Okay, so for example, H with NO3, there's your nitrate polyatomic ion. That's a strong acid, that's nitric acid. Two hydrogens with the sulfate polyatomic ion, that's the sulfuric acid. These are very strong acids. Also H with a Cl or H with a Br, HF, these are all acidic, all right? And in contrast, we could say not CH4, he has hydrogens, but he's not gonna give that away, right? If you removed one of the hydrogens and a positive charge, you would not be left with the polyatomic ion that you are familiar with. Also, for instance, not NaCl. There's not a hydrogen there, right? That should help guide you there. All right, next. Most bases have a negative charge that allows them to attract and react with the H plus ion. You can imagine nothing with a positive charge is going to attract another positive charge. So no bases will have a positive charge. And there's only one that are two that are neutral, right? So I'll put this in here. The two exceptions, which are NH3 and H2O, they can act as bases, although the H2O is not super basic. They have lone pairs, which act the same way. So for instance, I'll show you in water's case, you've got the oxygen, and because it's a bent molecule, as we remember, and because it's polar, you've got this partial minus on this side, partial positive on these sides, right? And you have this two lone pairs right here. So this partial negative charge on this side of the molecule attracts an incoming hydrogen ion, can attract an incoming hydrogen ion. where it can make a new bond using this lone pair of electrons right here. Okay, but these are the only two exceptions to the fact that we expect them to be negatively charged, right? So like as for instance, we would say we would expect hydroxide, obviously, to be a base because it has a negative charge. F minus is basic because it has a negative charge. Again, I'm not going to put that lone pair for the NH3 right out front there so you can see it. Those are all bases, but not, for instance, NH4 plus, because it has a positive charge. It would never attract a positively charged hydrogen, right? And not CH4. Again, this is a covalent compound. He doesn't have a negative charge. He doesn't have a lone pair, that kind of a thing. You with me so far? Okay. All right, hang on a second. Next, we will note that some, species can act as acids and bases, depending on the circumstances. Okay? It doesn't mean that it's going to act as an acid and a base at the same time. It just means when you put it in this situation, it'll act as an acid, or if you put it in that situation, it'll act as a base. Now, we just laid ground rules for what you can expect to see in an acid and what you can expect to see in a base. So you can look at that and say, well, if it's going to act as an acid and a base, then I can expect that, of course, it will have a spare hydrogen that can be removed. And it must have a negative charge to attract another hydrogen ion or lone pair to attract a hydrogen ion. So your examples here include water, because you can attract a hydrogen to make the hydronium, positively charged ion, and you can lose a hydrogen to make the hydroxide, negatively charged ion, And either one of those is a perfectly valid polyatomic ion that you're familiar with, so that those should be good. But then any of your polyatomics with a multiple charge, for instance, the sulfate has a -2 charge. So if I put just one hydrogen on there and I get the hydrogen sulfite ion, you can see it has another hydrogen. It could be removed to give you the sulfate polyatomic ion all by itself. And it has a negative charge. It could attract a hydrogen to make the H2SO4 molecule. It's the same thing with the phosphate polyatomic ion, which has a 3- charge. So we can have the dihydrogen phosphate polyatomic ion. We could have just the hydrogen phosphate polyatomic ion. In each of these cases, you see they have hydrogens and they have negative charges. Does that make sense? Okay, I've got a little image. This is actually from your 3rd lecture on acids and bases. I'm just gonna pop this in here. Okay, so I want you to look at this list of acids here. Can you see the hydrogen that could be removed in each of these cases? If you kind of go down the list, almost all of them list the hydrogen out front, which is appropriate because it's typical for us to list the cation in front of the anion, okay? Although they're not all exactly like that, right? H2O doesn't have a cation and an anion, and so on and so forth. This is one exception. They've written it like this, and the reason that they've put the hydrogen on the end is not because it's not the cation, but it's because in this structure, it's actually connected to that oxygen. So they're trying to show that connection there. Now this is the conjugate base. That's the base that's related to the acid, and we'll go into that in a little more detail in just a moment. But I want you to notice that almost all these have this negative charge that could attract the hydrogen. There's your one exception, it's neutral. Everything else has a 2- or a 1- charge here. There's your other exception that's neutral, and so on and so forth. Doesn't show you which ones of these are amphoteric, which is the fancy word for the things that can act as acids and bases. I should probably write this down. There's a way to describe that. That's right. So Sarah is making this observation. She says bases don't have to have a hydroxide ion in it. It just has to be negatively charged and in a way that allows them to attract and react with the hydrogen ion. Okay. So yes, this was our former definition that says you have to have the hydroxide. And now we're saying you don't actually have to have a hydroxide. If you have something else that will allow you to accept a hydrogen, then that's totally fine. So what we say is, well, in order to accept a hydrogen with a positive charge, it'll help if you have a negative charge that'll help you to attract. So you can see, here's the acids, these are the bases. Some of these, they have negative charges, but we don't really think of them as bases because that negative charge is not really strong enough to hold the hydrogen in water, right? And so they just are completely dissociated. And if you stick an acid, for instance, in with a solution of sodium chloride, that chlorine's not going to pick up the acid. You're just going to have a solution of acid and salt in water, and it'll still be acidic and salty as well, right? But it won't accept the hydrogen because it's not strong enough to hold it. But other ones are very strong. This will accept it and hold it in every case. These ones are weaker. We'll talk about what that means. Strong acids will basically completely dissociate in water. So they're all happy to give up a hydrogen. In this case, it's first hydrogen. And we should memorize, you're going to need to memorize this list of 7 strong acids for the exam. If it helps you to note, like these 3 here, HI, HBr, HCl, all of those are halogens. HF is the only one that's weak. But these are all very strong acids, like hydrochloric acid, as you might expect. And you've heard of nitric acid, that's the one made with nitrate, and sulfuric acid, that's the one made with sulfate. And the perchloric acid, I think, is probably the only one that'll be new to you. Anyways, okay, so this is how we define acids and bases. And just to practice, here we go. Our acids and bases worksheet. First page, first section, we're going to identify these substances as either acids, bases, both, or neither. And I'm going to hide that little cheat sheet there. Okay, help me out here. See what you can remember. NH3, is that going to be an acid or a base? Uh-oh. I have 1 vote for acid and 1 vote for base. Now it looks like he's got hydrogens. The question we have to ask ourselves, if we're trying to determine if it's going to be an acid or a base, is what happens if I accept a hydrogen and what happens if I remove a hydrogen, right? If I pick up a hydrogen versus subtract a hydrogen. Okay, let's see. If I pick up a hydrogen with a positive charge, then I won't have 3 anymore, I'll have 4, right? So I'll be NH4 with a positive charge. If I remove a hydrogen with a positive charge, then I won't have 3, I'll have 2, NH2. And since I removed a positive charge, I'll have a negative charge. And if you're not sure, this is just a really handy way to look at this and say, okay, which of these appears reasonable, or do they both appear reasonable? And you might say, Mary, we're only baby chemists. We have no idea what's reasonable. And my response to you is, oh, you've been baby chemist for a whole semester and now you're like toddler chemists. And you have an idea because you've memorized these structures and you've seen some of these structures. And if it's something you've never seen before, you should be very skeptical of it. I'm not going to give you anything you've never seen before. So in that case, you're going to look at this and say, okay, NH4 plus, you have seen that. That's the ammonium polyatomic ion you memorized, like way back at the beginning. So this should seem like a reasonable pathway. We feel good about this guy. But at NH2 minus, have you guys ever seen that before? Does it look uncomfortable? Does it make you go, I don't like that? Right? So we have not seen this before. Yeah, it does elicit a degree of like, wait a second, what is that? So this is not okay. It does not do that. It does just this. And that tells us, because it accepts this hydrogen, that tells us that NH3 is a base, right? So if you were paying very close attention and you memorized every one of these on the list, then you could just say, oh yes, I memorized NH3 is a base. But if you are not a very good memorizer, or if you thought, I don't want to bother with that, you can always do this and say, okay, what happens if I add a hydrogen? What happens if I try to donate one? And use that and your experience in this class. It should give you the right answer. Okay? Just want to give myself a little bit more room. Okay, what about HPO4 2 minus? Okay, Sarah and Nicole say both. And again, we're going to play the same game. Look, if I give it an H plus, or if I remove an H plus, what can I expect? And if I give it an H plus, it'll have an extra H, so it'll have two H's, PO4, and then it'll have one less negative charge, so it'll be H2PO4 minus. Is that okay? Yeah, that's just the dihydrogen phosphate polyatomic ion you memorized. And if I remove an extra hydrogen, then I'll have one less hydrogen here, and I'll have, since I remove a positive charge, it'll be even one more negative, and I become this PO4 3 minus. Is that okay? Yeah, that's the phosphate polyatomic ion. So we went to, either direction, we're seeing familiar polyatomic ions. So either one of those is legal. In this case, I would be donating the hydrogen, so that would be acting as an acid. In this case, I would be receiving a hydrogen, in this case, acting as a base. So therefore, since that one is okay, either way, it does both. Okay. All right, what about HClO4? Acid. Yeah. It doesn't have a negative charge to attract another hydrogen, and there's only two exceptions to that rule, and this is not one of them, right? So it's just going to be an acid. Good. What about calcium CaOH2 here? Totally a base. Calcium hydroxide. Again, you're just going to ignore the calcium and be like, yeah, it's calcium, but the hydroxide there, that's going to act as a base in solution. The hydroxide ions will accept hydrogens. Good. What about the NH4 plus? Acid. Right, it's got hydrogen. It could remove it to make a neutral species, and a positive charge is never going to attract another positive charge. Okay, good. Excellent. Do you guys feel pretty good about these? Okay. Let's move on to the next step, because it'll help, I think, solidify this. What I want you to see, what the next step is talking about, is conjugate acids and bases. And this is where you see, oh, some of these are related, okay? So for instance, when we went from the NH3 to the NH4 plus, we said the NH3 is acting as a base because it's accepting a hydrogen. And then we say, if I'm just evaluating NH4 plus, this is an acid because hypothetically, of course, it can lose that hydrogen. We can remove the hydrogen ion, and you would be left with the NH3 species, right? So the NH3 and the NH4 plus are related. We call them conjugates. It's a conjugate acid-base pair where the NH4 plus is the acid, the NH3 is the base. And Depending on where it is in the reaction, we'll call one of them the acid of the reaction and the other one the conjugate base, or vice versa for that reaction. All right, so let's look at this. Let me bring in just an example. Now, acid-base reactions, there's always one acid and there's always one base, because if you're donating a proton, somebody else has to be accepting it, and vice versa. And then on the other side, there will be one conjugate acid and one conjugate base that is related to the original base and the original acid that you've started. So let's analyze this reaction and see if we can identify what is accepting a proton here, what is donating a proton here. Can you guys tell me which of these two things is acting as the acid? H2SO4 is the acid. It helps to know that this guy couldn't act as anything else. He doesn't have a negative charge, and there's only 2 neutral species that could ever act as a base. But if you weren't sure, then the other thing is to say, okay, well, what happened when we went to the product? Right, the H2SO4 became HSO4 minus. It lost a hydrogen and it lost a positive charge because now it's negatively charged. So clearly, because it lost its H plus, we're going to say it donated its H plus because it's not there anymore. You guys see that? And if the H2SO4 is the acid, that means that the H2O in this case must have been the base. So let's have a look at this and say, did that really, to be a base, you have to accept the H plus, which means I could expect that this is going to have an extra hydrogen and an extra positive charge. Does it have an extra hydrogen and an extra positive charge? Yes, it does, right? So you can tell that this was the acid because it lost an H plus, and this was the base because it gained an H plus. And now on this side, we can say, all right, well, this guy, he came from the acid, but if, for instance, I went backwards, he would have to accept the H plus to get here. So he would be like a base going backwards. So for this reaction, we're going to call him the conjugate base from this conjugate acid base pair here, right? They're related to each other. And if I was to go backwards again, I would have to lose that H plus ion to get back to water. And that means that I am the conjugate acid in this reaction. Does that make sense? Okay, let's try another one, a little bit more complicated. In this case, you have 2 amphoteric species on the left-hand side. Either one of them could act as acids or bases. In this reaction, it's shown doing this one thing. So in this reaction, which of these is acting as the acid? The water or the hydrogen sulfate? Excuse me. It's the hydrogen sulfate. Oh, Sarah's totally right. I love this observation. Sarah says it's kind of like oxidation and reduction. And that's a great observation. Like oxidation reduction, there's always both of them together, right? If there's oxidation, you know there's going to be reduction. Here, if there's an acid, you know there's going to be a base, right? In these reactions. And if you're oxidized going in the forward direction, then you're being reduced going in the backwards direction, right? So if you're an acid going in the forward direction, then you're a base going in the backwards direction. That's a great observation. It is exactly like that. Good. I think that's helpful. Okay, so on this one, you said H2SO4, but there's not actually an H2SO4. I think you meant HSO4 minus. Is that right, Sarah? In this case, this is still your acid. It could have been either, but again, we just look at these guys and say, well, the product sulfate has lost a hydrogen, so it must have been donated to somebody else. That makes it the acid. And let's see, that means H2O must have gained it. Did it gain a hydrogen and a positive charge? Yes, it did. So then that H2O in this case must be the base, right? And the base goes to form the conjugate acid. And of course, the acid goes to form the conjugate base. All right, let's try one more here from the lecture notes for funsies. I like this one because it doesn't even have water in it, right? What is going on here? Good. Acid is HCl. It can't really be anything else, right? HCl is not going to be a base ever. It's a very strong acid. That means that this has got to be the base. Let's look at our products and see if that's true. Does the HCl, does it lose the hydrogen when it makes the product here? Yes, it does. There's only chloride remaining. So this is going to be your conjugate base. Does the NH3, does it pick up an extra hydrogen ion? Yes, it does. So that makes this your conjugate acid. Does this help kind of solidify what to look for when we're trying to determine if something's an acid or a base? I hope it helps a little bit. Okay, we're gonna do, I'm gonna do one more just from your worksheet and then we can move on here. So this is straight out of your worksheet, section 2. Identify acids, bases, conjugate acids, and conjugate bases here. And there's 2 other examples, but I think we're pretty good on this. So we've got this reaction. It looks like sodium carbonate reacts with HCl to make sodium hydrogen carbonate and NaCl. It's a little bit different because I'm not showing you just ions here. This is the whole molecular equation instead of kind of a net ionic equation here. So, all right, Sarah says, and I trust her, she says HCl is the acid and the base is Na2CO3. How did you make that determination, Sarah? That's right. Okay, so going from HCl to the product over here, NaCl, there's no longer an H on that Cl, so it must have lost it. Okay, so that makes this our conjugate base. If we're right, that means we should expect to see that this guy picked up an extra hydrogen. Did that happen? Na2CO3. Yep, he's got an extra hydrogen right there. Perfect. So of course that makes this guy the conjugate acid. All right, how do you feel about these? Awesome, awesome, awesome. All right, that's it for this lecture. I'll see you in the next one where we'll do acid-base calculations.